Okay. So we had an exam question, a question on one of the exam questions. So we had a half-wave rectifier, three-phase half-wave rectifier. So I will erase all of this because I don't need it. So we have a circuit that looks like this. So we have a source here, a source here, and a source here. These are the three-phase sources. And again, how does a half-wave rectifier look? We just have one diode in series with a source and a load, right? But here I flipped the diode, right? So then that's my RC circuit here, right? And then I can do this for the second one, and do this for the third one. Okay? So this is my circuit. So if I just have one of these, I know that I know that what we studied was this case, right? This, and then we put the capacitor. So without the capacitor, if the input voltage looked like this, the output voltage looked like this red waveform without the capacitor. And if I've put the capacitor and sized it properly, I know that in my next positive half cycle, I should size the capacitor such that I charge the capacitor during this period, for example, until here, and then the capacitor will be feeding my resistive load for the rest of the period until the next positive half cycle, right? So this is the output voltage would look like this black waveform, right? Okay, so the output voltage would look like this, right? So that's for this case. What if I flip the diode? Hmm? Yeah, so it will do the same thing, but in the negative half cycle, right? So it's exactly the same thing, but negative half cycle. So that's why. So don't get confused. Simplify it to things you know. So this thing is nothing but three of those, with waveforms shifted by a certain value. In this case, there are three-phase sources, so the waveforms will be shifted by 120 degrees, right? So how do we do this? So these are three waveforms shifted by 120 degrees, and we look at the phase voltages because again, when the diode is on, I'm connecting the phase voltage to the output, right? This is, even though this is a three-phase rectifier, but I'm connecting the phase voltages to the output when any of the diodes are on, right? So if diode A is on, if this is the most negative voltage, this diode will be on. This is the most negative voltage, this diode will be on. This is the most negative voltage, this diode will be on, right? So that's the sequence of operation. So now let's see what's happening here. So if we're saying that if it's the most negative, the corresponding diode, if it's the most negative voltage, the corresponding diode will be on, and then the others will be off because they cannot be on at the same time, right? If they're on at the same time, what happens? If these two are on, I have a short circuit across my source, right? So what I'm doing here is this rectification, but in the negative half cycle, and I'm doing it based on the phase voltage. So these are my VA, VB, and VC voltages. These are my line voltages. I don't need them, right? In this picture that we use for the phase line voltages, I don't need my line voltages here at all. The output will be across my phase voltages. And what will the output look like for one period? The output will follow the most negative waveform value. So it will follow phase B here, follow phase C during this period, follow phase A during this part, follow phase B during this part. So this will be the output value, output voltage. The peak value, peak output voltage, peak negative, the maximum output negative output voltage will be the Vmax here, right? This is Vmax. In the exam, I think it's 90, or it's not clear. I think on the scan it's not clear, but let's say it's 90. Okay, if it's 90, I'm trying to ask you what is the value of delta V, right? Output voltage ripple with respect to max value, right? I think that was the question. So if Vmax is the max value is Vmax, okay? Output voltage ripple, what's the is the delta V here? So I want this point, this value in terms of Vmax. This value in terms of Vmax is where these two waveforms intersect. These two waveforms intersect where? Here, right? So this is what? If this is if this is a sine wave here, this is 180, and then another, I guess, 30 degrees. So this is which be what? 210. So sine 210 is what? I think it's half, right? Sine 210. Negative half. I mean, so half. So this point here is minus Vmax over 2. So this is Vmax over 2 as a magnitude, and this is Vmax. So I'm just trying to say what is the value of delta V with respect to the peak voltage. So it's half. Yes.
The capacitors, there's no exponential case here?
No, again, there is. I think the question says without before the capacitor, right? So, huh? Before the capacitor. I think before the capacitor. I don't remember the reading. I remember that because with the capacitor you cannot do that. With the capacitor, the delta V will change, right? You're gonna size the capacitor for a specific delta V. So now you have a certain delta V. Now you're gonna add a capacitor. That capacitor will reduce the delta V. So you know that the delta V now is half of V maximum. If it's 90, then it's 45 volts. So then now your new delta V spec should be, I don't know, 20 volts, 10 volts, whatever it is. So if you know delta V spec, which is, and you choose it as 10 volts, for example, and you will need to calculate the delta Q, which is the area under the current curve, and you will need to then you will use C equals delta Q over delta V to calculate the capacitance. This is if you want to use my equations, right? So, or you can use but textbook doesn't have equation for equation for this for the three-phase half-wave rectifier. Three-phase half-wave, it does not. I don't think the textbook has an equation for that. So in this case, you would need to calculate if I ask you to calculate the capacitance for a new value of delta V, then you would need to look at the current waveform. So the current waveform will look like this, right? This is the actual current waveform because the voltage, if this is a resistive load, this is the actual current waveform. So what does the capacitor do? The capacitor will absorb. Again, this is something I will not ask you about in this chapter because the text doesn't have an equation for it. But in the next chapter, in chapter 6, we will talk about something like this. So this is your output voltage waveform, correct? If this is my output voltage waveform, let me erase here. Remember what we want to do is find delta Q over delta V. Delta V is a spec, 10 volts, for example, now because we know that originally it's 45. So for me to find the capacitance, I need delta Q. How do I find delta Q? I have the voltage waveform or the current waveform look the same. They look exactly they look like this, right? So if the current waveform looks like this, what I would like to do is this current waveform here is this is what's coming from this is the load current waveform, right? This is the load current waveform here that's going into the resistor. So it's in this direction because the voltage will be in the opposite direction, right? So the current will go in this direction, voltage in the opposite direction. So what's going to happen? I would like to put a capacitor here. If I put a capacitor here, what's going to happen? What will happen is that I expect the waveform to look something like this. You know, my delta V or delta I in this case, they will look the same, will be reduced. Instead of from this peak to peak of the black, it will be the peak to peak of the red, right? Because I chose a new delta V to be 10 volts. How do I find delta Q in this case? So delta Q will be where? The current through the capacitor, right? It's the area of, so that would have been the current that would need to flow in the capacitor to eliminate all the AC components from the resistor. Do we agree? Okay, I want to see lower AC component in the resistor, right? Now I have what? This is a waveform. Is this DC? This black waveform. Is this a DC waveform? The black waveform? it's not pure DC, right? It's a waveform that has AC content plus DC content, right? Remember, anything that's not pure DC, it will have AC content and some DC content. What is my objective? My objective is to push or have DC current flow through my load, okay? So I will have to assume something. I will assume that I want DC current to flow through my load only, which means that I've eliminated my ripple completely, right? That's the ideal case. For that to happen, where will this current flow? I mean, this current is this. I mean, without this capacitor, this is the current that's flowing, right? If I put this capacitor, the AC component of this current will flow in the capacitor, and the DC component will remain. It will go to my load. Is what's going to go to my load, right? So how do I remove the AC component of this black waveform? We'll go through it quickly now because again, it's not something I will explain a lot more in chapter 6. But let's let me draw this. Erase this. I have this waveform. I'll draw it again. I want some space. So I'll draw it. I'll draw a waveform like this. For example, this is a waveform that has some AC content plus DC content, right? I would like to put a capacitor, and the objective of putting the capacitor there is that all the AC current will flow through the capacitor, and then the rest of the current will flow, the DC current will flow through the load. So how do I remove the AC component from this waveform? Again, it's a waveform with AC values and DC values. How do I remove the DC component from that waveform? From a waveform like this, how would I remove the average value, DC component?
Make it lower than that.
Exactly. How? What do you mean make it lower? Move this graphically. I mean graphically, I would move this way until what? Average waveforms, their area on top of the zero axis equals the area below the zero axis, right? So I would take this waveform and shift it up. By how much? By until, of course I didn't draw it properly here. I should have moved it further. I should have done something more like this. Right? So this is now my ideal capacitor current. Ideal capacitor current. That's assuming that I've removed all ripple, right? Why is that? Because I've removed all average value from this waveform. And I've taken all the AC component. This is only the AC component. Do you agree now that this waveform is only the AC component that's contained in this waveform? Okay? Do we agree or not?
Yeah.
Okay, so this is the waveform. I gave you any funky waveform. Look, as long as it's periodic, right? Any periodic funky waveform. This is what the current looks like in the system. Okay? I'm asking you to put a capacitor to eliminate the current ripple. I mean, to absorb the current ripple, so that absorb and supply the current ripple, so that I maintain a nice DC voltage. That's the objective, right? I can give you any looking waveform. It looks like this. You would remove the average value, and then you'll be left with the AC component. This AC component is what you want to flow in the capacitor, right? Because if you make that AC component flow in the capacitor, not to the load, then the load will only contain the DC component. Okay, that's the logic, right? So then how do you go about sizing the capacitor that can allow you to do this? You would find this delta Q is the area here, or the area here. Doesn't matter, right? It's either the area this is delta Q, or this is delta Q, right? So it's either this, you calculate this area or this area. After you calculate this area or this area, you plug it in this equation, in the numerator of this equation. The delta V will be plugged in. This is a spec. This is a number you came up with. You know that the circuit already gives you a delta V of 45 volts, assuming this is 90. Right? Because this is half the value of this. So now I would choose a delta V of 10 volts. So now I have my delta Q, and you choose a specific delta V, and you should be able to calculate the C. Does it make some sense? Okay. I don't know. You don't. I mean, this is not what I asked in the exam. In the exam, I just asked the difference between this point and this point, basically. I asked for the relationship between the delta V.
The capacitor wasn't even there in the exam question, you just asked to put one, or asked us what to put there.
Yeah, exactly. Because we didn't cover chapter 6, which where we go through all of this in detail. In chapter 6, we're going to be drawing lots of current waveforms and finding areas, etc., etc. But it's the same. I'm doing that in the context of DC to DC converters in chapter 6, but it's the same. I mean, it's the same as chapter, the rectifier, the half-wave rectifier with the capacitor. It's exactly the same. They're all, sizing of reactive elements is exactly the same in any circuit. Just draw the circuit without the reactive element. The objective of the reactive element is to remove the AC component. If it's going to remove the AC component of current, you put the capacitor. If you're going to remove the AC component of voltage, you put the inductor. That's it. And then you draw the corresponding waveform after you've removed the DC component, or after you've put all the AC component in the reactive element. So put all the AC component of current in the capacitor. Put all the AC component of voltage across the inductor. And then what you're going to be left with is the DC component. Now that you have the AC component of voltage across the inductor, or the DC component of current through a capacitor, then you can size it. It does not matter which type of circuit. It does not matter. They're all the same. At the end of the day, the capacitor and the inductor are physical elements that behave the same way. You put charge, voltage rises. You remove charge, the voltage goes down. Okay? So the exam question is this. Are you okay with it? Sure? Okay. Okay. So that being said, we'll